Okay, our next speaker is Guillermo. Guillermo is also from Coimbra, and Guillermo, the presentation of Guillermo is also related with Markov, but a different theorem from Markov, but are really close. Guillermo, we will talk about probably the most beautiful theorem of Markov, which is the theorem of Markov related with the monotonicity of the series of the orthogonal polynomials and its extension. Thank you, Guillermo.
Okay, thank you. Good morning. So I'm going to be speaking about some properties of zeros of orthogonal polynomials. So in principle, one could speak about many properties like the distribution or the asymptotics, or one could interpret the zeros are charges that are in equilibrium with certain potential. But in this case, we're interested in studying the monotonicity of the zeros with respect to certain parameters. So we assume, similarly to previous presentation, that the measure depends on a parameter, and so the zeros of the associated orthogonal polynomial can be interpreted as function of the parameter, and so we ask ourselves how to behave with respect to this parameter. In this regard, it was Markov who first produced three significant results. So in this talk, we are interested about this following result that were proved in 1886. In this case, we assume that we got a measure. This measure depends on this parameter, and is absolutely continuous with respect to this other measure, and the parameter falls into this omega. And so the result is very simple in its form, and it states that the zeros of the associated orthogonal polynomials are increasing function of the parameter, provided that this function here is increasing function of x on the real interval the measure is supported. So here simply this quantity is very straightforward to compute, right? It's simply derivative with respect to the parameter, and it gives us the monotonicity of the zeros. And we also got the second part, whenever this quantity is decreasing, then the zeros are decreasing function. So we may make use of this result to obtain the monotonicity of the zeros of certain family of orthogonal polynomials. In particular, here we have the Jacobi polynomial, right? This is the usual measure, and here we got two parameters, alpha and beta. And we compute these quantities, and we obtain that this function is decreasing with respect to x, and this is increasing, and so we obtain that the zeros of this polynomial decrease with alpha and increasing with beta. This is another example. This is the Ham polynomial. They also depend on two parameters, alpha and beta, and similarly we obtain that the zeros decrease with alpha and the zeros increase with beta. So the beauty of the result is simplicity, right? The philosophy is that the measures are simple, and so the monotonicity of the zeros should also be obtained in a simple way. Because as a matter of fact, one could have made use of the explicit expression of the orthogonal polynomials to derive the monotonicity of the zeros with respect to these parameters. But the computation are unnecessarily cumbersome and complicated when it all falls on the measure. Also notice that in this case, the measure with respect to the absolute continuity we have is continuous. In this case, it would be like the best measure. I mean this mu. And in this case, for the half polynomial, is discrete. So the original proof by Markov only considered like the Riemann case, and later on it was extended by Sego to consider any particular any arbitrary measure. And this proof was given, I believe, or at least it's in the book in the volume that was published in 1939. And it relies, this proof of this extension of the original Markov theorem, it relies heavily on this property that we call Gaussian quadrature. Like we got a measure, right? And we want to approximate the integral of this measure In order to do so, we consider, well, we want to make it valid for a certain degree of up to a certain degree of a polynomial, right? And so in order to achieve this, we fix polynomial. We consider it zeros, and these zeros will work as the nodes of the quadrature. And then we have some associated weight that are strictly positive, and this is relevant. And so it holds this formula that is valid for any p, for any polynomial of degree at most 2n minus 1. And here we see that we are evaluating the p on the zeros of the orthogonal polynomial. So the important part of this result is this is as good as it can get, this quadrature, because for example, if we were to consider polynomial, if we were to assume that this is true also for polynomial of degree 2n, then we could put here pn squared. So pn squared would have a positive integral. This would be strictly positive. But here we would be evaluating pn squared on its zero, so it should be zero. So this is as good as it gets. And the thing is that this proof relies heavily on this two nice property, that is that this weights, these lambdas are positive, and this is true up to a maximum degree. But the issue with this, though it's an elegant result, is that when we are trying to extend this result of Markov to other classes of orthogonal polynomials, and we try to mimic the procedure in this proof, it happens that the quadrature formula that are associated to the rest of the classes of orthogonal polynomial are not as good as this one. So, for example, we wouldn't have this positivity of the weight, or we wouldn't have that this result is valid to this degree. So, for this reason, it happened that this extension of Markov theorem on the variation of zero was stopped. There weren't any kind of extension due to this inability. So, in order to produce an extension, the first step, well, was taken by Kenya, our dear Kenya, and he got rid of the quadrature and decided to try to obtain the similar result, the same expression, but in a simpler way, setting aside the quadrature and finding a simpler argument that depended solely on the fundamental properties of the polynomial, mainly on the main definition, so that we are able to extrapolate them to the rest of the class of polynomial. And in particular, in 2019, he proved this extension of the Markov theorem in the real line to the class of parallel orthogonal polynomials on the unit circle. So in this case, we got a measure that is supported on the unit circle, right? And the unit circle parameterized by this theta. And well, in this case, as Alexandre told, the parallel polynomial, they lie on the unit circle. So the monotonicity in this case is not that they increase or decrease, it's that they move counterclockwise or clockwise, depending on, again, this quantity, which is the same as in the original Markov theorem, the real line, is increasing or decreasing respectively. So in this way, we obtain that the Markov theorem remain essentially valid in this context. And well, okay, the idea of the proof is kind of straightforward, and it relies on this simplicity of the zeros of the associated orthogonal polynomial, and well, on expressing this the monotonicity, the variation of the zero in this form, and operating. Okay, but the proof itself is pretty technical. So if you are interested, you may check the paper itself. But the important part is that this procedure can be replicated up to a point, and we may extrapolate the ideas to extend the result to the class of multi-orthogonal polynomials in the real life. So now I'll speak a little about the multiple orthogonal polynomials on the real line. I'll talk about the definition, then some particular results about some families about the monotonicity of zeros of some families of multiple orthogonal polynomials. And then I'll show how, with these ideas, we can obtain another extension of Markov zero to this class of polynomials that, well, up to a point, more or less extends the results that were obtained in a particular way. So, well, these multiple orthogonal polynomials on the real line, they're also called Hermite-Padé polynomials because they appear in Hermite-Padé approximation, right? Well, they're relevant in number theory, and the information of the zeros is important. But the issue was that the results of the zeros were scarce, and they were very particularized to the families of polynomials considered. Well, and in particular, well, it was this problem of extending the Markov zero was stated by Ismail. Okay, and so the definition is as follows. In this case, we got we don't have only one measure. We had m measures in general supported on the real line, and well, in principle, you don't need to be absolutely continuous or anything like that. But for the purpose of this talk, we assume that it's absolutely continuous with respect to this weight function. And now, instead of fixing index, we fix a partition. Each of these number here is associated to each of the measure, and they all sum the degree of the polynomial that we will consider. And so, a polynomial of degree n, this degree, is said to be a multiple orthogonal polynomial on the real line with respect to this measure and this partition if it satisfies this series of conditions that depend on this k, right, which is associated to the measures, and simply states that the orthogonality in this case is distributed between amongst the different measures. And so we see that it's orthogonal, so to say, up to degree nk minus 1 if nk is the index associated to the measure k. Okay, so in general, this polynomial may not exist. It depends on the measure and on the relation of the sets of measure that we are considering. And well, this is some notation. We say if this polynomial exists, then the partition is said to be normal. And if we fix a set of measure, and for a partition we got the existence of the polynomial, we say that the set of measure form a perfect set. Well, in particular, there's this condition here that ensures that a partition is normal and is related to this weight, these weights that that construct the measures. And well, it's related to this so-called algebraic Chebyshev system, and we say that this system, or an arbitrary system of n function, is algebraic Chebyshev if in an arbitrary linear combination of the function has at most n minus 1 zeros, but the definition itself is not relevant. The idea is that if we got that this set of function satisfy this AD property, then the partition is normal. And interestingly, there exists some classes of sets of measure for which every partition satisfies this AD property, and so they are perfect, and they are the interesting classes of sets of measure that are studied in this context. So in this case, the more studied flavor of set of measure are the Angelesco and the Nikishin. So in the case of the Angelesco set of measure, it's happened that all the measure has disjoint support, and in the case of the Nikishin set, it's quite the opposite of all the supports coincide and they are related by some transform, but I'm not going to go into much detail about Nikishin sets of measure, and we will focus mainly on the Angelesco type multiple orthogonal polynomial and the extension to Markov to this kind of context. So as I was saying, we got a certain measure, and then their supports are pairwise disjoint, real interval, of course, and these are some properties. So we said that every partition was normal, okay? And also this is important for the proofs, as I stated before. We got that the n simple, the n zeros of the multiple orthogonal polynomial are simple. And also it happens that if nk is the index associated to the measure k, there are nk zeros located on ik if ik is the support of the k measure. And so we are able to decompose the multiple orthogonal polynomial in this way, and this gives us some certain properties of this Q. And in particular, we obtain that this Q cannot behave like an orthogonal polynomial with respect to its associated measure, but modified through the rest of the Qs, which are which hold the zeros in the other intervals. And well, these properties are relevant for the proof itself of the Markov extension, but we won't go into much detail. And this is the simultaneous Gaussian quadrature that I was talking at the beginning. So in this case, we also have like a similar formula that is valid for every measure. Here, the measure are in this L, and we got weight for each L. So it's simultaneous quadrature because the nodes are the same, but the weights, of course, change for each measure. But it has two main issues, as I was saying at the beginning, and that's the reason that these quadrature are weak, is that it does not go up to the maximum degree. So it goes only to n plus nl, if nl is the index associated to the L measure, -1. In the other case, we got n plus n minus 1. And also, it happens that the weights in this case, are only positive if they belong to the support, to the interval, if they're associated to the nodes that belong to the interval where the measure is supported. And the rest of the weights are alternating in sign, so that's why the classical arguments by Sego were not able to be replicated in this case. And now speak about some families of multiple orthogonal polynomial and some particular results about their monotonicity. So here we fix two measures, and here we consider the Jacobian-Jelesco polynomials that results when considering these two measures that are defined from a to 0, and this a is negative, and from 0 to 1. And of course, it constitutes a generalization of the Jacobi polynomial. So in principle, at the beginning, there exists an implicit formula for the Jacobian-Jelesco polynomial, of course, and it was introduced in this way as a generalization of the Jacobi polynomials. But later it was found out that it corresponded to this multiple orthogonal polynomial with respect to these measures. And only recently, some particular results about the monotonicity of the zeros of this polynomial were obtained. This author, in particular, obtained only monotonicity of the zeros, but for the so-called diagonal case, when n1 equal n2, and in particular, of course, n1 could be different than n2, and in particular, he obtained that the zeros increase with this alpha, which lies at the left boundary of the leftmost measure, decrease with this gamma that is on the right, and also with this beta, which is in the middle. It happens that the zeros on this interval decrease, and the zeros of this interval increase with respect to beta, whenever the case is, whenever a equal -1, so we are in the symmetric case. And later on, recently this year, this author improved a little this result and obtained the same result, but for the non-symmetric case, but still only on the diagonal case. So for this result, they employed the explicit formula, but in this case, we are dealing with multiple orthogonal polynomials, and we got different measures. The explicit formula itself, it's more complicated, so we are not able to obtain the same results as in the case of the classical Jacobi polynomial, where the expression were simpler, and so the computation were simpler. So here they are only able to obtain properties in the more symmetric way when n1 equals n2. And well, also there exists another two families of multiple orthogonal polynomial that generalize the Laguerre polynomial and the Hermite polynomials, and they are related also to the Jacobi-Laguerre polynomial that I introduced before by asymptotic relation. So the monotonicity of the zeros of the Jacobi-Laguerre polynomial are related to this one. So one obtains the monotonicity of the zero with respect to the other one. So in order to try to extend these particular results, not only to these families, to arbitrary families, we can proceed in a similar way that in the case of the orthogonal polynomials on the unit circle, and we obtain this Markov extension to Angelesco type multiple orthogonal polynomials on the real line. So in this case, consider a measure, as I was speaking about, and well, of course, we got the parameter again in the weight, and this time we obtain a slightly worse result than in the case of the orthogonal polynomials on the unit circle, because well, apart from this usual condition that one imposed on the measure for the monotonicity, one also need to impose this condition that is kind of like this one, but instead of derivating with respect to the parameter, we derivate with respect to x, and we need to impose that it is decreasing so that everything falls, and we may reobtain the Markov theorem. So that's why I call it a partial extension. But despite this inconvenience, we are able to improve a little the results of this particular family. In this case, of course, we obtain very simply the derivative, and we see that this function increases with respect to x, this is decreasing with respect to x, and this also is increasing with respect to x is alpha is negative, so we obtain the usual condition that Markov assumes. And of course, maybe I didn't explicitly talk about this, we're imposing the classical Markov condition in each measure, because in this case we got different measures. But the problem here, though this is straightforward, is that if we want to compute this, the fact that this derivative with respect to x is decreasing, there exists some restriction of the parameters. So in principle, the polynomial are defined with these parameters greater than -1, but in order for this quantity to be decreasing with respect to x, and so the result to be valid, we need to impose this, and so we obtain a partial improvement of the other results, because in the other result we only considered it was only considered the diagonal case. In this case, we obtained the fact that the zeros increase with respect to alpha, decrease with respect to gamma, and increase with the left endpoint a, but only when this restriction of the parameters are considered. Despite this, I believe that this condition maybe can be taken out, and so we could be able to obtain an adequate, more real Markov extension to this type of polynomials. And that is all I wanted to speak about. Thank you.
Thank you so much, Guillermo. Questions and remarks?
Yes, thank you for the nice talk. I have a question regarding the proof of your theorem. which method do you use? Do you go through the Gaussian formulas, or do you use this approach of Kenya? Or, yeah,
yes.
Small comment. Yeah, thank you.
Yeah, no, the issue was that, let me go back to, the issue was that in this case, what I wanted to show here is that if we compare it with the Gaussian quadrature, it's weaker, because here we got that some weights are positive, but they are alternating in sign, and also we don't have that it's true for 2n plus 2n minus 1, as in the classical case. And these two properties, the fact that the weights were all positive, and that the fact that the formula is valid up to the maximum degree were crucial for the proof that provided Sego. So in this case, we are not able to replicate those arguments, and so for this particular case, we go with the more elemental procedure that was based on the result that Kenny obtained for the orthogonal polynomials. That was the idea.
Thank you. More questions or remarks? If no more questions and remarks, so let me just say it's a remark. Yes, and that condition that appears are related with the fact that a certain matrix is a Z matrix, and this results is a partial results because it's not submitted and not published, and we only will send the results which prove that indeed, also in this case, Markov's theorem remains valid. If you not, there are many good papers and recent papers just for very particular case of two measures, and in a very particular case, that is the symmetry case. If you have a Markov theorem, all this is solved, and we solve also, well, the problem was collected by Ismail, but it's a very well-established problem to extend Markov theorem to multiple orthogonal polynomials and using number theorem and so. If not more questions, thanks again, Guillermo. Guillermo is starting, well, he will start his PhD next year, okay? So he is presenting our first word, which is a partial result for a partial student. Okay, thank you so much.